What if I told you that half the universe's matter has gone missing? Not just a small fraction, but an entire half, enough to rewrite our understanding of the cosmos. This isn't science fiction. It's one of the greatest mysteries in modern cosmology, the missing baryon problem. Baryons, the building blocks of everything we see, stars, planets, even you and me, make up only a fraction of the universe's total matter. Yet when scientists tally up all the baryons they can observe, half of them are unaccounted for. Where could they be hiding, and why does this matter? The answer could reshape our understanding of the universe itself. In this video, we'll dive into 25 clues that could finally solve this cosmic puzzle. From the vast cosmic web connecting galaxies to the faint whispers of hot gas detected by X-ray telescopes, each clue brings us closer to uncovering the truth. This isn't just about filling in a gap in our knowledge, it's about piecing together the story of how the universe works, from the smallest particles to the largest structures. So, if you've ever wondered what lies beyond the stars or how the universe holds itself together, you're in the right place. By the end of this journey, you'll not only understand the mystery of the missing baryons, but also see why solving it could unlock secrets about the very fabric of reality. Stay with us because the answers are closer than you think, and they're more fascinating than you can imagine. Now, let's turn our attention to the first clue in this cosmic mystery, the cosmic web. Picture the universe not as a random scattering of galaxies, but as an intricate tapestry, woven together by an enormous network of filaments. These filaments, made up of gas and dark matter, stretch across the cosmos, connecting galaxies like threads in a vast, invisible spiderweb. This structure is known as the cosmic web, and it's one of the most fascinating frameworks in the universe. But here's where it gets even more intriguing. Scientists believe that within these filaments lies a potential hiding place for the missing baryons. Specifically, they suspect that the warm-hot intergalactic medium, or WHIM for short, could be the key. The WHIM is a diffuse, superheated gas that fills the spaces between galaxies, and it's so faint and spread out that it's incredibly difficult to detect. Think of it like trying to spot a single drop of water in a foggy sky. It's there, but it's nearly invisible to our current tools. This warm-hot intergalactic medium is thought to contain a significant portion of the missing baryons trapped within the cosmic web's filaments. The gas is so hot that it emits X-rays, but these emissions are so faint that they've only been detected in small amounts. This makes the WHIM a prime suspect in the case of the missing baryons. If we can find a way to map this elusive gas more effectively, we might finally uncover where half the universe's matter has been hiding all along. The cosmic web isn't just a beautiful structure, it's a potential treasure map guiding us toward the answers we've been searching for. And as we continue to explore this vast network, we'll see how it ties into the next clues in our journey to solve the missing baryon problem. Now, let's shift our focus to another fascinating piece of the puzzle, the role of dark matter. While the cosmic web gives us a framework for where baryons might be hiding, dark matter adds another layer of intrigue to this cosmic mystery. Dark matter, as you might know, is an invisible substance that makes up about 27% of the universe's total mass and energy. It doesn't emit, absorb, or reflect light, which makes it impossible to observe directly. But its presence is undeniable because of its gravitational effects on the visible universe. So, how does dark matter tie into the missing baryon problem? Well, dark matter's immense gravitational pull shapes the universe on the largest scales. It forms massive halos around galaxies and clusters, creating gravitational wells that can trap and hold onto baryonic matter. Think of it like a cosmic net. Dark matter's gravity pulls in gas and other baryonic material, keeping it hidden in regions that are difficult for us to observe. These regions, often located in the outskirts of galaxies or in the vast spaces between them, could be where a significant portion of the missing baryons are lurking. But here's where it gets even more interesting. Dark matter doesn't just hide baryons, it also influences how they behave. The gravitational interplay between dark matter and baryonic matter can heat up gas, push it into intergalactic space, or even compress it into dense filaments within the cosmic web. This dynamic relationship means that dark matter isn't just a passive player in the universe, it's actively shaping where and how baryons are distributed. However, detecting these hidden baryons is no easy task. Because dark matter doesn't interact with light, the regions it dominates are often shrouded in darkness, making it challenging to observe the baryons trapped there. Scientists rely on indirect methods like studying the gravitational lensing effects of dark matter or analyzing the motion of galaxies to infer where these hidden baryons might be. As we piece together the role of dark matter in this cosmic puzzle, it becomes clear that understanding its influence is crucial to solving the missing baryon problem. The interplay between dark matter and baryonic matter is a delicate dance, one that shapes the universe in ways we're only beginning to comprehend. And as we move forward, we'll see how this relationship ties into the next clues in our search for the universe's missing matter. Now, let's turn our attention to a powerful tool in the search for the missing baryons, X-ray observations. While dark matter's gravitational influence gives us hints about where baryons might be hiding, X-ray telescopes like Chandra have allowed us to peer into the universe in a whole new way. These telescopes detect faint emissions from hot gas, revealing a hidden world of baryonic matter that's otherwise invisible to us. Galaxy clusters, some of the largest structures in the universe, are filled with incredibly hot gas. This gas, heated to millions of degrees, emits X-rays that can be detected by telescopes like Chandra. These observations have uncovered vast reservoirs of baryonic matter in the form of this hot gas, often referred to as the intracluster medium. It's a significant discovery because it shows that a large portion of the missing baryons could be hiding right in the heart of these massive clusters. One of the key breakthroughs came when scientists analyzed the X-ray emissions from galaxy clusters and found that the amount of hot gas far exceeded what was previously thought. This gas doesn't just sit idly, it interacts with the galaxies and dark matter within the cluster, creating a dynamic environment where baryons are constantly being redistributed. The sheer volume of this gas suggests that it could account for a substantial fraction of the universe's missing baryons, but the implications go even deeper. The temperature and density of this hot gas provide clues about the history of the universe itself. By studying these X-ray emissions, scientists can trace how gas has been heated and moved around over billions of years, offering insights into the processes that shape the cosmos. For example, the Chandra telescope has revealed how supermassive black holes at the centers of galaxies can heat surrounding gas, pushing it out into the intracluster medium and contributing to the missing baryon problem. What makes X-ray observations so crucial is their ability to uncover baryons in regions that are otherwise invisible. While optical telescopes show us the stars and galaxies, X-ray telescopes reveal the hot, diffuse gas that fills the spaces between them. This gas, though faint, is a critical piece of the puzzle, and its discovery has reshaped our understanding of where baryons might be hiding. As we continue to explore the universe with X-ray telescopes, each observation brings us closer to solving the missing baryon problem. The faint glow of hot gas in galaxy clusters is more than just a cosmic curiosity, it's a vital clue in our quest to understand the universe's hidden matter. And as we move forward, we'll see how these discoveries connect to the next pieces of the puzzle, bringing us ever closer to uncovering the full story of the missing baryons. Now, let's shift our focus to another fascinating clue in the search for the missing baryons, the Sunyaev-Zel'dovich Effect. This phenomenon, named after the scientists who first described it, offers a unique way to trace baryonic matter in the universe. It occurs when hot gas in galaxy clusters distorts the cosmic microwave background radiation, the faint afterglow of the Big Bang. This distortion creates a subtle but detectable signature that astronomers can use to map the distribution of baryons in these massive structures. The cosmic microwave background radiation is like a snapshot of the early universe, a relic from a time when the cosmos was just a hot, dense soup of particles. As this radiation travels through space, it encounters galaxy clusters filled with hot gas. When the radiation passes through this gas, some of its energy is transferred to the electrons in the gas, causing a slight shift in the radiation's wavelength. This shift, known as the Sunyaev-Zel'dovich Effect, leaves a distinct imprint that can be measured by sensitive instruments. What makes this effect so powerful is its ability to reveal baryons in regions that are otherwise difficult to observe. Unlike X-ray observations, which rely on detecting emissions from hot gas, the Sunyaev-Zel'dovich effect works by measuring the impact of that gas on the cosmic microwave background. This means it can detect baryons even in less dense or cooler regions of galaxy clusters, where X-ray emissions might be too faint to observe. One of the most exciting discoveries using this effect came when astronomers combined it with X-ray data to create detailed maps of galaxy clusters. These maps showed that the distribution of baryons in clusters is far more complex than previously thought. The hot gas isn't evenly spread, it's clumped and stretched in ways that reflect the dynamic interactions between galaxies, dark matter, and the intracluster medium. This uneven distribution suggests that baryons are constantly being moved around, making them harder to track and account for. The Sunyaev-Zel'dovich effect has also provided insights into the evolution of galaxy clusters. By studying how the effect changes over time, scientists can learn how gas has been heated and redistributed as clusters grow and merge. This information helps us understand not just where baryons are hiding today, but how they've been moving and evolving over billions of years. As we continue to refine our observations using this effect, it's becoming clear that the missing baryons are not just hiding in plain sight. They're woven into the very fabric of the universe's largest structures. The Sunyaev-Zel'dovich effect is a powerful tool in our quest to solve this cosmic mystery, and it's helping us piece together the story of where the universe's missing matter has gone. With this clue in hand, we're ready to explore another piece of the puzzle, the Lyman alpha forest, a phenomenon that reveals the presence of hydrogen gas in the vast reaches of intergalactic space. This next clue will take us even deeper into the cosmic web, where the missing baryons may be hiding in plain sight. Now, let's venture into the cosmic depths to uncover another intriguing clue, the Lyman alpha forest. This phenomenon, though it might sound like something out of a science fiction novel, is a real and powerful tool in our search for the missing baryons. It all begins with distant quasars, some of the brightest objects in the universe, whose light travels billions of years to reach us. As this light journeys through space, it passes through vast clouds of hydrogen gas scattered across the cosmos. When the light from these quasars encounters hydrogen gas, something fascinating happens. The gas absorbs specific wavelengths of light, creating a series of dark lines in the quasar's spectrum. These lines, known as the Lyman alpha forest, are like cosmic fingerprints, revealing the presence and distribution of hydrogen gas along the line of sight. Each line corresponds to a different cloud of gas at a different distance from us, creating a forest of absorption features that astronomers can study in detail. What makes the Lyman alpha forest so valuable is its ability to map the large-scale structure of the universe. The hydrogen gas responsible for these absorption lines is part of the cosmic web, the vast network of filaments that connects galaxies and galaxy clusters. By analyzing the patterns in the Lyman alpha forest, scientists can trace the distribution of this gas, which is believed to account for a significant portion of the missing baryons. One of the key insights from studying the Lyman alpha forest is that much of this hydrogen gas exists in a diffuse, low-density state. This makes it incredibly difficult to detect using traditional methods, as it doesn't emit much light or heat. However, the absorption lines in quasar spectra provide a way to see this gas indirectly, offering a glimpse into regions of the universe that would otherwise remain hidden. Recent observations using powerful telescopes have revealed that the Lyman alpha forest is far more extensive than previously thought. The gas clouds stretch across billions of light years, forming a complex web of filaments that permeates the universe. This discovery has led scientists to estimate that a substantial fraction of the missing baryons could be hiding in these diffuse clouds, woven into the fabric of the cosmic web. But the story doesn't end there. The Lyman alpha forest also provides clues about the history of the universe. By studying how the absorption lines change with distance and therefore with time, astronomers can learn how the distribution of hydrogen gas has evolved over billions of years. This information helps us understand not just where the missing baryons are today, but how they've been moving and changing as the universe has expanded and evolved. As we piece together the clues from the Lyman alpha forest, it's becoming clear that the missing baryons are not lost, they're simply hiding in plain sight, spread across the vast reaches of intergalactic space. This next clue brings us one step closer to solving the cosmic mystery of the missing baryons, and it sets the stage for our next exploration: the role of supercomputer simulations in predicting where these elusive particles might be hiding. Now, let's shift our focus to a powerful tool that has revolutionized our understanding of the cosmos: supercomputer simulations. These simulations are like cosmic time machines, allowing scientists to recreate the evolution of the universe from its earliest moments to the present day. By modeling the complex interactions of dark matter, gas, and radiation, these simulations provide a virtual laboratory where we can test theories and predict where the missing baryons might be hiding. One of the most remarkable aspects of these simulations is their ability to trace the formation of the cosmic web. As the universe expanded and cooled after the Big Bang, tiny fluctuations in density grew over time, pulled together by gravity. Supercomputers can simulate this process, showing how dark matter formed the backbone of the cosmic web, while baryonic matter, the ordinary matter we're made of, flowed along these filaments, eventually clumping into galaxies and galaxy clusters. But here's where it gets even more fascinating. These simulations don't just show us where baryons ended up, they also reveal where they might still be hiding. For example, they predict that a significant amount of baryonic matter exists in the form of warm hot intergalactic medium, or WHIM. This diffuse gas, heated to temperatures of hundreds of thousands of degrees, is spread across the vast voids between galaxies. While it's too faint to detect directly, simulations suggest it's a key reservoir for the missing baryons. Another insight from these simulations is the role of feedback mechanisms. When stars explode as supernova or supermassive black holes unleash powerful jets of energy, they can push baryons out of galaxies and into intergalactic space. Simulations show how these processes redistribute baryons over billions of years, making them harder to detect in traditional observations. What's truly groundbreaking is how these simulations align with real-world observations. For instance, the distribution of gas predicted by simulations matches the patterns seen in the Lyman alpha forest, reinforcing the idea that much of the missing baryons are hiding in the cosmic web. They also help explain why X-ray telescopes have detected faint emissions from hot gas in galaxy clusters, another piece of the puzzle. As we continue to refine these simulations with more powerful computers and better data, they're becoming an indispensable tool in the search for the missing baryons. They not only guide astronomers to where they should look, but also help us understand the complex processes that have shaped the universe over billions of years. This brings us to our next clue, where we'll dive deeper into the warm-hot intergalactic medium and explore why this elusive gas is so difficult to detect and how scientists are working to uncover its secrets. Now, let's take a closer look at one of the most elusive components of the cosmic web, the warm-hot intergalactic medium, or WHIM. This mysterious gas, which fills the vast spaces between galaxies, is believed to hold a significant portion of the universe's missing baryons. But what exactly is the WHIM, and why has it been so challenging to detect? The WHIM is a diffuse, high-temperature gas heated to hundreds of thousands of degrees. Unlike the cold, dense gas found within galaxies, the WHIM is spread thinly across the universe, making it incredibly faint and difficult to observe directly. It forms as a result of the cosmic web structure, where gravity pulls matter into filaments and nodes, leaving behind vast, empty regions. As gas flows along these filaments, it gets heated by shocks and collisions, creating the WHIM. One of the reasons the WHIM is so hard to detect is its temperature. While it's hot enough to emit X-rays, the emissions are extremely weak because the gas is so spread out. Traditional telescopes struggle to pick up these faint signals, especially against the background noise of the universe. Additionally, the WHIM doesn't emit much visible light, making it nearly invisible to optical telescopes. To overcome these challenges, scientists have turned to indirect methods. For example, they study the absorption of light from distant quasars as it passes through the WHIM. This creates a unique fingerprint in the quasar's spectrum, revealing the presence of hydrogen and other elements in the gas. Another approach involves looking for the faint X-ray emissions predicted by simulations, using advanced instruments like the Chandra X-ray Observatory. Despite these efforts, the WHIM remains one of the most difficult components of the universe to study. Its diffuse nature and faint signals mean that detecting it requires cutting-edge technology and innovative techniques. However, the potential payoff is enormous. If we can confirm the presence of the WHIM and measure its properties, it could solve a major piece of the missing baryon puzzle. This brings us to our next clue, where we'll explore how supermassive black holes might be influencing the distribution of baryons, adding another layer of complexity to this cosmic mystery. Now, let's shift our focus to another fascinating piece of the puzzle, the role of supermassive black holes. These cosmic giants, found at the centers of most galaxies, are not just mysterious voids, they're incredibly powerful engines that can shape their surroundings in profound ways. But how exactly do they tie into the missing baryon problem? Supermassive black holes are known for their immense gravitational pull, but they also release enormous amounts of energy as they consume matter. This energy doesn't just vanish, it gets channeled into the surrounding gas, heating it to extreme temperatures. In some cases, this process can even push gas out of galaxies entirely, sending it streaming into intergalactic space. This heated gas becomes part of the warm-hot intergalactic medium, or WHIM, which we've already discussed as a potential hiding place for missing baryons. But here's the twist: the energy from supermassive black holes can make this gas even harder to detect. When gas is heated to such high temperatures, it emits faint X-rays that are easily lost in the background noise of the universe. What's more, the outflows driven by black holes can spread baryons over vast distances, making them more diffuse and difficult to trace. This means that even if the baryons are out there, they might be so thinly spread that our current telescopes can't pick them up. Scientists are using advanced simulations and observations to better understand this process. For example, they've found that the energy from black holes can create bubbles of hot gas around galaxies, which then mix with the surrounding intergalactic medium. These bubbles might contain a significant amount of the missing baryons, but detecting them requires incredibly sensitive instruments and precise measurements. The interplay between supermassive black holes and the missing baryons adds another layer of complexity to this cosmic mystery. It shows how the universe's most extreme objects can influence the distribution of matter on the largest scales. This leads us to our next clue, where we'll explore how the early universe during the epoch of reionization might have played a role in redistributing baryons and leaving some of them unaccounted for today. Now let's journey back in time to one of the most transformative periods in the universe's history, the epoch of reionization. This era, which began roughly 400 million years after the Big Bang, marked the birth of the first stars and galaxies. But it wasn't just a time of cosmic creation, it was also a period of dramatic change for the distribution of baryons, the ordinary matter that makes up everything we see. During the early universe, baryons were mostly in the form of neutral hydrogen, a gas that was cool and relatively easy to detect. However, as the first stars ignited and galaxies began to form, their intense ultraviolet light started to ionize this hydrogen. This process, known as reionization, stripped electrons from hydrogen atoms, turning the gas into a hot, ionized plasma. This shift had a profound effect on the universe's structure, but it also made baryons much harder to track. The energy from these early stars and galaxies didn't just ionize hydrogen, it also pushed baryons into new regions of space. Some of this matter was blown out of galaxies entirely, while other portions were heated and spread across vast intergalactic distances. This redistribution of baryons during the epoch of reionization could explain why some of them seem to be missing in modern observations. They're not gone. They've just been scattered and transformed in ways that make them difficult to detect with current technology. One of the challenges in studying this period is that the light from the first stars and galaxies is incredibly faint and has been stretched into the infrared part of the spectrum by the expansion of the universe. This makes it hard to observe directly. However, scientists have found clever ways to piece together clues about this era. For example, they study the absorption lines in the light from distant quasars, which reveal the presence of ionized hydrogen gas. These observations suggest that the epoch of reionization was a chaotic and dynamic time, with baryons being pushed and pulled in all directions. Another key piece of the puzzle comes from simulations of the early universe. These models show how the first stars and galaxies could have created bubbles of ionized gas, which then expanded and merged, eventually filling the universe with ionized hydrogen. While these simulations help us understand the process, they also highlight how much we still have to learn about the distribution of baryons during this critical period. The epoch of reionization reminds us that the universe is constantly evolving, and the baryons we're searching for today might have been reshaped by events billions of years ago. This clue takes us one step closer to solving the missing baryon problem, but it also raises new questions about how the early universe influenced the cosmos we see today. Next, we'll explore another intriguing possibility. Could the missing baryons be hiding in the extended halos of galaxies, where they're too faint for our telescopes to detect? Let's find out. Now, let's turn our attention to the outskirts of galaxies, where the mystery of the missing baryons might be hiding in plain sight. Galaxies are more than just the bright, star-filled disks we see in images. They're surrounded by vast, extended halos of gas and dust that stretch far beyond their visible boundaries. These halos, though faint and difficult to observe, could be a key hiding place for the baryons we've been searching for. The idea is that these galactic halos contain a significant amount of baryonic matter in the form of hot, diffuse gas. This gas is so thinly spread out and so faint that it doesn't emit much light, making it nearly invisible to our telescopes. But just because we can't see it doesn't mean it's not there. In fact, simulations of galaxy formation suggest that a large portion of a galaxy's baryons might reside in these halos, rather than in the stars and gas within the galaxy itself. One reason these halos are so hard to detect is that the gas within them is extremely hot, often reaching temperatures of millions of degrees. At such high temperatures, the gas emits X-rays, but these emissions are incredibly faint and easily drowned out by other sources of X-rays in the universe. To make matters more challenging, the gas in these halos is also very diffuse, meaning it's spread out over such a large area that its signal becomes even weaker. Despite these challenges, astronomers have found ways to probe these elusive halos. One method involves studying the light from distant quasars as it passes through the halos of foreground galaxies. As the quasar light travels through the halo gas, some of it gets absorbed, creating distinct absorption lines in the quasar's spectrum. These lines act like fingerprints, revealing the presence and properties of the gas in the halo. Observations like these have provided strong evidence that galactic halos do contain significant amounts of baryonic matter, even if we can't see it directly. Another approach is to use computer simulations to model how galaxies form and evolve. These simulations show that as galaxies grow, they pull in gas from their surroundings, which then settles into their halos. Over time, some of this gas cools and falls into the galaxy, fueling star formation, while the rest remains in the halo, too hot and diffused to collapse. This process suggests that galactic halos could act as reservoirs of baryons, storing matter that might otherwise go unnoticed. The challenge now is to develop new technologies and techniques that can help us detect this faint halo gas more effectively. Future telescopes with greater sensitivity to X-rays and ultraviolet light could provide the breakthrough we need. By peering deeper into these halos, we might finally uncover the missing baryons and solve one of the universe's most enduring mysteries. As we continue our search, let's consider another fascinating possibility. Could cosmic winds, driven by supernova and black holes, be blowing baryons out of galaxies and into the vast reaches of intergalactic space? That's our next clue to explore. Now, let's shift our focus to the powerful forces that could be scattering baryons across the cosmos, cosmic winds. These winds, driven by the explosive energy of supernova and the immense gravitational pull of supermassive black holes, might be playing a crucial role in redistributing baryonic matter far beyond the boundaries of galaxies. When a massive star reaches the end of its life and explodes as a supernova, it releases an enormous amount of energy. This energy doesn't just vanish, it creates shock waves that push gas and dust outward, generating powerful winds that can travel at incredible speeds. These winds carry baryonic matter with them, sweeping it out of the galaxy and into the surrounding intergalactic space. Over time, this process can strip galaxies of a significant portion of their baryons, leaving them hidden in the vast, empty regions between galaxies. Supermassive black holes lurking at the centers of galaxies also contribute to these cosmic winds. As these black holes consume matter, they release tremendous amounts of energy in the form of radiation and jets of particles. This energy can heat up the surrounding gas, creating outflows that push baryons outward. In some cases, these outflows are so powerful that they can eject baryons entirely from the galaxy, sending them into the intergalactic medium. The result is a cosmic redistribution of matter. Baryons that were once concentrated within galaxies are now spread out across the universe, making them much harder to detect. This process could explain why so much of the universe's baryonic matter seems to be missing. It's not gone, but rather scattered far and wide by these relentless cosmic winds. Detecting these winds and the baryons they carry is no easy task. The gas they transport is often extremely hot and diffuse, emitting faint signals that are easily overshadowed by brighter sources. However, astronomers have developed techniques to study these outflows. For example, by observing the spectra of distant galaxies, they can identify the signatures of gas being pushed out by winds. These observations provide valuable clues about the role of cosmic winds in the missing baryon problem. As we piece together the evidence, it becomes clear that cosmic winds are a significant factor in the distribution of baryons throughout the universe. They remind us that galaxies are not isolated islands of matter, but are deeply connected to the larger cosmic web, constantly exchanging material with their surroundings. With this clue in mind, let's turn our attention to another potential hiding place for the missing baryons: the hot gas within galaxy clusters, known as the intracluster medium. Could this be where the rest of the universe's baryons are hiding? Let's find out. Now, let's venture into the heart of galaxy clusters, where another key piece of the missing baryon puzzle might be hiding: the intracluster medium. This vast reservoir of hot gas, filling the spaces between galaxies within a cluster, could hold a significant portion of the universe's elusive baryons. But what exactly is the intracluster medium, and why is it so important in our search? Galaxy clusters are the largest structures in the universe, bound together by gravity and containing hundreds or even thousands of galaxies. But galaxies aren't the only things filling these clusters. Between them lies a sea of incredibly hot gas, heated to temperatures of millions of degrees. This gas, known as the intracluster medium, is so hot that it emits X-rays, making it detectable by telescopes like Chandra and XMM Newton. The intracluster medium is a treasure trove of baryonic matter. In fact, it's estimated that the gas in the intracluster medium outweighs all the stars in the cluster's galaxies combined. This means that a substantial amount of the universe's baryons could be hiding right here in the spaces between galaxies. But why is this gas so hard to account for in our cosmic inventory? One reason is its extreme temperature. The gas in the intracluster medium is so hot that it's fully ionized, meaning its atoms have lost their electrons. This makes it invisible to traditional optical telescopes, which rely on detecting light from stars and cooler gas. Instead, we need X-ray telescopes to see it. Even then, the gas is so diffuse that its signals are faint, blending into the background of the universe. Another challenge is understanding how this gas got there in the first place. Over billions of years, as galaxies formed and evolved, they released gas into their surroundings through processes like supernova explosions and black hole activity. This gas was then heated and swept up into the intracluster medium, where it remains today. But the exact mechanisms of how this gas is distributed and how much of it exists are still areas of active research. Despite these challenges, astronomers have made significant progress in studying the intracluster medium. By analyzing the X-rays it emits, they've been able to map its distribution and estimate its mass. These observations suggest that the intracluster medium could account for a significant fraction of the missing baryons, potentially solving a large part of the mystery. So, while the intracluster medium might not be the easiest place to look for missing baryons, it's certainly one of the most promising. Its vast reservoirs of hot gas remind us that the universe is full of surprises, and that sometimes the answers we seek are hiding in the most unexpected places. With this clue in mind, let's turn our attention to another fascinating possibility: the role of magnetic fields in shaping the distribution and detectability of baryons. Could these invisible forces be hiding even more of the universe's missing matter? Let's explore this next. Now, let's shift our focus to an invisible yet powerful force that could be playing a key role in the missing baryon mystery: magnetic fields. These unseen forces permeate the universe, shaping the behavior of matter in ways we're only beginning to understand. But how exactly could magnetic fields be hiding baryons from our view? Magnetic fields are everywhere in the cosmos, from the smallest scales of planets and stars to the vast expanses of galaxy clusters and intergalactic space. They're generated by the movement of charged particles like electrons and protons, and can influence how matter behaves on both small and large scales. In the context of the missing baryon problem, magnetic fields might be subtly altering the distribution and detectability of baryonic matter, making it harder for us to observe. One way magnetic fields could hide baryons is by affecting the motion of gas in the universe. For example, in galaxy clusters, magnetic fields can channel hot gas along specific paths, creating intricate patterns that are difficult to map. This gas, which is part of the intracluster medium we discussed earlier, might be pushed into regions where it's harder to detect, either because it's too diffuse or because it's shielded by other material. Another possibility is that magnetic fields could influence the way baryonic matter emits or absorbs light. In some cases, magnetic fields can polarize light, changing its orientation and making it harder to interpret the signals we receive from distant objects. This polarization effect could obscure the presence of baryons, especially in regions where magnetic fields are particularly strong, like around black holes or in the turbulent environments of star-forming regions. Magnetic fields might also play a role in heating gas to extremely high temperatures, as we've seen in the intracluster medium. When gas is heated, it becomes ionized, meaning its atoms lose their electrons. This ionized gas is invisible to optical telescopes, and while X-ray telescopes can detect it, the faint signals can easily blend into the background. Magnetic fields could be contributing to this heating process, making the gas even harder to observe. But detecting and measuring these magnetic fields is no easy task. Unlike electric fields, magnetic fields don't interact directly with light, making them invisible to most telescopes. Instead, astronomers rely on indirect methods, such as studying the polarization of light or observing the behavior of charged particles in space. These techniques are still being refined, and much about cosmic magnetic fields remains a mystery. Despite these challenges, researchers are making progress. For example, studies of synchrotron radiation, which is emitted by electrons spiraling around magnetic field lines, have provided valuable insights into the strength and structure of magnetic fields in galaxy clusters and other cosmic environments. These observations suggest that magnetic fields could indeed be playing a significant role in shaping the distribution of baryons, potentially hiding them from our view. So, while magnetic fields might seem like an unlikely culprit in the missing baryon mystery, their influence on the cosmos is undeniable. They remind us that the universe is full of hidden forces, shaping the behavior of matter in ways we're only beginning to uncover. As we continue to explore this clue, we're reminded that solving the missing baryon problem will require us to look beyond the obvious and consider the subtle, often invisible, forces at work. With this in mind, let's turn our attention to another intriguing possibility: the impact of cosmic voids, those vast, empty regions of the universe that might hold more secrets than we realize. Could these seemingly barren spaces be hiding some of the universe's missing baryons? Let's find out. Now, let's venture into one of the most fascinating and mysterious aspects of the cosmos: cosmic voids. These vast, seemingly empty regions of the universe stretch across millions of light years, appearing as gaps in the cosmic web where galaxies are sparse or entirely absent. But don't let their emptiness fool you. These voids might hold crucial clues to the missing baryon problem. Cosmic voids are not completely empty. While they lack the dense clusters of galaxies we see elsewhere, they are filled with extremely diffuse gas and dust. This gas, though incredibly thin, could account for a significant portion of the universe's missing baryons. The challenge lies in detecting it. Because the gas in these voids is so spread out, it emits very little light, making it nearly invisible to traditional telescopes. One way astronomers have tried to uncover these hidden baryons is by studying the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang. As this radiation passes through cosmic voids, it interacts with the sparse gas, leaving subtle imprints that can be detected. These imprints, known as the Sunyaev-Zel'dovich Effect, provide indirect evidence of the gas's presence, even if we can't see it directly. Another approach involves looking at how light from distant quasars is absorbed as it travels through cosmic voids. The absorption lines in the spectra of these quasars, known as the Lyman alpha forest, reveal the presence of hydrogen gas. In cosmic voids, this gas is so diffuse that its absorption lines are incredibly faint, but they still offer a glimpse into the baryonic content of these regions. Simulations of the universe also suggest that cosmic voids could be hiding more baryons than we realize. These simulations show that as the universe expands, baryons are pushed into these low-density regions where they remain in a state that's difficult to observe. The gas in voids is often too cool to emit X-rays or too faint to be detected by optical telescopes, making it a perfect hiding place for missing baryons. But why does this matter? Understanding the distribution of baryons in cosmic voids could help us solve the missing baryon problem by filling in the gaps literally. If a significant portion of the universe's baryons are spread out in these voids, it would explain why they've been so hard to find. It also highlights the importance of developing new observational techniques and technologies to probe these elusive regions more effectively. Cosmic voids remind us that the universe is full of surprises. What appears to be empty space might actually be teeming with hidden matter waiting to be discovered. As we continue to explore these vast, mysterious regions, we're reminded that solving the missing baryon problem requires us to look in the most unexpected places. With this in mind, let's turn our attention to another intriguing possibility: the role of neutrinos, those elusive particles that might hold the key to understanding how baryons interact with the rest of the universe. Could neutrinos be obscuring our view of the missing baryons? Let's explore this next clue. Now, let's shift our focus to a particle that's as elusive as it is fascinating: the neutrino. These tiny, nearly massless particles are everywhere, streaming through the universe, and even through you at nearly the speed of light. While neutrinos aren't baryons themselves, they might play a surprising role in the mystery of the missing baryons. Neutrinos are incredibly difficult to detect because they rarely interact with other matter. They pass through planets, stars, and even entire galaxies without leaving a trace. But their ghostly nature doesn't mean they're unimportant. In fact, neutrinos could be influencing the behavior of baryonic matter in ways we're only beginning to understand. One way neutrinos might obscure our view of baryons is through their interactions with other particles. When neutrinos collide with baryons, even though it's rare, they can transfer energy, altering the state of the baryonic matter. This interaction could make baryons harder to detect, especially if they're scattered or heated in ways that make them invisible to our current observational tools. Another possibility is that neutrinos could be affecting the distribution of baryons on cosmic scales. As neutrinos move through the universe, their gravitational influence, though tiny, could subtly shift the positions of baryonic matter. Over billions of years, these small nudges might cause baryons to accumulate in regions we're not actively searching, or to spread out in ways that make them harder to spot. Interestingly, neutrinos themselves are a product of baryonic processes. They're created in enormous quantities during nuclear reactions, like those in the cores of stars or during supernova explosions. This means that where there's baryonic matter, there's likely a flood of neutrinos. By studying neutrinos, we might gain indirect clues about the behavior and location of baryons. But here's the challenge: detecting neutrinos is no easy task. Specialized detectors, often buried deep underground to shield them from other particles, are required to catch these elusive particles. Even then, we're only able to detect a fraction of the neutrinos passing through. This makes it difficult to fully understand their role in the missing baryon problem. Despite these challenges, neutrinos offer a unique window into the universe's hidden workings. By studying their properties and interactions, we might uncover new insights into how baryons are distributed and why they've been so hard to find. Neutrinos remind us that sometimes the key to solving a cosmic mystery lies in the most unexpected places. With this in mind, let's turn our attention to another intriguing possibility: the missing baryons in our own cosmic backyard. Could some of the universe's missing matter be hiding within the local group of galaxies, including the Milky Way and Andromeda? Let's explore this next clue. Now let's zoom in closer to home, our cosmic neighborhood, the local group. This collection of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, might hold some of the answers to the missing baryon problem. Could the baryons we've been searching for be hiding right here, in the very galaxies we call our own? the local group spans millions of light years, but it's still a relatively small corner of the universe. Within this region, galaxies like the Milky Way and Andromeda are surrounded by vast halos of gas and dust. These halos are thought to contain significant amounts of baryonic matter, but they're incredibly faint and diffuse, making them difficult to detect with our current technology. One possibility is that baryons are hiding in these galactic halos, spread out in a way that makes them nearly invisible. The gas in these halos is often too cool to emit much light and too thin to block the light from background objects. This means traditional observation methods like optical or X-ray telescopes might not be able to spot them easily. Another intriguing idea is that baryons could be hiding in the form of warm hot gas between galaxies in the local group. As galaxies move through space, they can pull gas along with them, creating streams and clouds of material that stretch across intergalactic space. These structures, often referred to as the circumgalactic medium, could contain a significant portion of the missing baryons. But detecting this gas is no simple task. It's often too faint to see directly, and its signals can be drowned out by the brighter light from stars and galaxies. To overcome this, astronomers use indirect methods like studying the absorption of light from distant quasars as it passes through the local group. These observations can reveal the presence of gas that would otherwise go unnoticed. Interestingly, simulations of the local group suggest that a large fraction of baryons could indeed be hiding in these hard-to-see regions. The interplay of gravity, galactic winds, and other forces might have pushed baryons into these diffuse areas where they remain hidden from our view. So, while the local group might seem like a familiar place, it's still full of mysteries waiting to be uncovered. By studying our own galactic neighborhood in greater detail, we might finally find some of the missing baryons that have eluded us for so long. With this in mind, let's turn our attention to another fascinating clue: the role of cosmic rays. Could these high-energy particles be playing a part in obscuring baryons from our view? Let's explore this next piece of the puzzle. Now, let's shift our focus to another intriguing piece of the puzzle: cosmic rays. These high-energy particles, zipping through space at nearly the speed of light, might be playing a surprising role in the mystery of the missing baryons. But how exactly do they fit into this cosmic detective story? Cosmic rays are not rays in the traditional sense. They're actually particles, like protons and atomic nuclei, that have been accelerated to incredibly high energies. When these particles collide with gas in space, they can ionize it, stripping electrons from atoms and turning the gas into a plasma. This ionization process can make the gas harder to detect, especially if it's already faint and diffuse. Imagine trying to spot a faint light in a foggy room. If someone suddenly turns on a bright lamp, the fog becomes even harder to see through. In a similar way, cosmic rays can light up the gas in a way that makes it blend into the background, hiding it from our telescopes. This could explain why some baryons remain elusive. They're not necessarily missing, but rather obscured by the effects of these high-energy particles. Another fascinating aspect of cosmic rays is their ability to heat the gas they interact with. When cosmic rays collide with gas particles, they transfer energy, raising the temperature of the gas. This heating can cause the gas to expand and become even more diffuse, further complicating our efforts to detect it. In regions where cosmic rays are abundant, like near supernova remnants or active galactic nuclei, this effect could be particularly strong, making baryons even harder to find. But here's where it gets even more interesting. Cosmic rays don't just interact with gas, they can also influence the magnetic fields in space. As these charged particles move through magnetic fields, they can create turbulence, which in turn affects how gas is distributed. This turbulence can scatter and redistribute baryons, potentially pushing them into regions where they're even more difficult to observe. So, while cosmic rays might seem like a small piece of the puzzle, their impact on the universe's baryonic matter is anything but minor. By ionizing gas, heating it, and influencing magnetic fields, they could be playing a significant role in hiding baryons from our view. As we continue to explore the missing baryon problem, it's clear that cosmic rays are a key factor to consider. But they're not the only one. Next, let's dive into another fascinating clue: the role of feedback mechanisms in redistributing baryons across the cosmos. How do processes like star formation and black hole activity shape the distribution of matter in the universe? Let's find out. Now, let's turn our attention to another fascinating piece of the puzzle: feedback mechanisms. These processes, driven by the explosive energy of star formation and the immense power of black holes, play a crucial role in shaping the universe, and they might be hiding baryons in plain sight. When stars form, they don't just quietly appear. The process is violent and energetic, often accompanied by powerful winds and supernova explosions. These events can blow gas and dust out of galaxies, redistributing baryons into the surrounding intergalactic space. Imagine a giant cosmic fan scattering particles far and wide. This means that some of the baryons we're searching for might not be where we expect them to be. They could be spread out across vast regions, making them much harder to detect. But stars aren't the only players in this cosmic drama. Supermassive black holes lurking at the centers of galaxies also contribute to this feedback process. When these black holes feed on surrounding matter, they release enormous amounts of energy in the form of jets and radiation. These outflows can push gas out of galaxies, sometimes even halting star formation altogether. This process, known as quenching, not only affects the evolution of galaxies but also scatters baryons into the intergalactic medium, where they become diffuse and difficult to observe. What's particularly intriguing is how these feedback mechanisms create a kind of cosmic recycling system. Baryons ejected by star formation or black hole activity might eventually cool and fall back into galaxies, only to be ejected again in a continuous cycle. This constant movement makes it challenging to pin down the exact location of baryons at any given time. They're not missing, they're just on the move, caught in a dynamic dance driven by the forces of the universe. Feedback mechanisms also have another surprising effect. They can heat the gas they interact with, making it harder to detect. When gas is heated to extremely high temperatures, it emits light in wavelengths that are difficult for our telescopes to pick up. This means that even if baryons are present, they might remain invisible to us simply because they're too hot to observe clearly. So, while feedback mechanisms might seem like a side effect of cosmic processes, they're actually a key piece of the missing baryon puzzle. By redistributing and heating baryons, they make these particles far more elusive than we might expect. But the story doesn't end here. Next, we'll explore another clue that might help us uncover the missing baryons: the role of gravitational lensing and how it could be distorting our view of the universe. Stay tuned. Now, let's shift our focus to a phenomenon that bends not just light but our understanding of the universe itself: gravitational lensing. This cosmic trick of the light, predicted by Einstein's theory of general relativity, occurs when massive objects like galaxies or galaxy clusters warp the fabric of space-time. As light from distant objects passes through this warped space, it gets bent, magnified, or even distorted, creating effects that can either reveal or obscure the baryons we're searching for. Gravitational lensing acts like a natural telescope, amplifying the light from objects that would otherwise be too faint to see. But here's the twist: it can also distort the appearance of baryonic matter, making it harder to identify. Imagine looking at a reflection in a funhouse mirror. The image is still there, but it's stretched, twisted, or split into multiple copies. Similarly, baryons hidden behind massive objects might appear smeared or duplicated, blending into the background and escaping detection. One of the most intriguing aspects of gravitational lensing is its ability to reveal the presence of dark matter. Since dark matter doesn't emit light, we can't see it directly. But its gravitational influence bends light, creating lensing effects that allow us to map its distribution. This, in turn, gives us clues about where baryons might be hiding. If dark matter is clumped in certain areas, baryons could be gravitationally bound to it, lurking in the same regions but remaining invisible to our telescopes. However, gravitational lensing isn't just a tool for discovery, it's also a potential source of confusion. The distortions it creates can make it difficult to determine the true location and amount of baryonic matter. For example, a single galaxy might appear as multiple images due to lensing, complicating our efforts to measure its baryon content accurately. This means that some of the missing baryons might not be missing at all. They could simply be hiding in plain sight, camouflaged by the very effects we use to study them. Despite these challenges, gravitational lensing offers a unique window into the universe's hidden structures. By carefully analyzing these distortions, astronomers can piece together the distribution of both dark and baryonic matter, bringing us closer to solving the missing baryon problem. But the story doesn't end here. Next, we'll explore how dark energy, the mysterious force driving the universe's expansion, might be influencing the distribution and detectability of baryons. Stay with us as we uncover yet another layer of this cosmic mystery. Now, let's turn our attention to one of the most mysterious forces in the cosmos, dark energy. This enigmatic energy, which makes up about 68% of the universe, is responsible for the accelerated expansion of space itself. But how does this rapid expansion affect the missing baryons we've been searching for? The answer lies in the way dark energy reshapes the very fabric of the universe. As dark energy drives the universe to expand faster and faster, it creates vast distances between galaxies and galaxy clusters. This expansion doesn't just stretch space, it also stretches the distribution of baryonic matter. Imagine a balloon being inflated. As it grows, the dots drawn on its surface move farther apart. Similarly, baryons are being spread out over increasingly larger volumes of space, making them more diffuse and harder to detect. This could explain why some baryons seem to be missing. They're not gone, but rather diluted across the cosmos. But there's another layer to this puzzle. The accelerated expansion caused by dark energy also affects the way we observe baryons. As light from distant objects travels through this expanding space, it gets stretched into longer, redder wavelengths, a phenomenon known as redshift. This redshift can make it more challenging to detect certain types of baryonic matter, especially in the form of warm, hot intergalactic gas, which emits faint signals that are already difficult to observe. The farther away these baryons are, the more their light is stretched and the harder they become to spot. Interestingly, dark energy's influence doesn't stop there. It also impacts the formation of large-scale structures in the universe, like the cosmic web. As the universe expands, the gravitational pull of dark matter and baryons struggles to counteract the repulsive force of dark energy. This tug-of-war slows down the growth of cosmic structures, potentially leaving some baryons in regions where they're less concentrated and more challenging to detect. In other words, dark energy might be subtly rearranging the cosmic map, hiding baryons in plain sight. Despite these challenges, understanding dark energy's role is crucial to solving the missing baryon problem. By studying how it shapes the universe's expansion and influences the distribution of matter, astronomers can refine their search strategies and develop new techniques to uncover these elusive particles. And as we continue to explore this cosmic mystery, we're reminded that the universe is full of surprises, each one bringing us closer to unraveling its deepest secrets. Next, we'll dive into how cosmic dust might be obscuring our view of baryons, adding yet another twist to this fascinating story. Stay tuned. Now, let's shift our focus to another fascinating piece of the puzzle, cosmic dust. This seemingly mundane material, made up of tiny particles scattered throughout the universe, might be playing a bigger role in the missing baryon problem than we initially thought. Cosmic dust isn't just a nuisance for astronomers trying to get a clear view of distant stars. It could also be hiding baryons right under our noses. Cosmic dust is made up of tiny grains of carbon, silicon, and other elements, often no larger than a fraction of a millimeter. These particles are found everywhere, from the vast emptiness of interstellar space to the dense regions surrounding stars and galaxies. While they might seem insignificant, their ability to absorb and scatter light makes them a major obstacle for astronomers. When light from distant objects passes through clouds of cosmic dust, it gets absorbed or redirected, effectively blocking our view of what lies beyond. This means that baryons which emit or reflect light could be obscured by these dusty veils, making them invisible to traditional observation methods. But how exactly does cosmic dust hide baryons? Imagine trying to look through a foggy window. You can see shapes and movement, but the details are blurred or completely hidden. In the same way, cosmic dust acts like a cosmic fog, masking the presence of baryonic matter. This is especially problematic when we're trying to detect faint signals from warm, hot intergalactic gas or other diffuse forms of baryons. The dust absorbs their light, making it nearly impossible to observe them directly. Interestingly, cosmic dust doesn't just block light. It also re-emits it at longer wavelengths, such as infrared. While this might sound like a silver lining, it actually complicates things further. The re-emitted light is often too faint or spread out to provide clear information about the baryons hidden behind the dust. This means that even with advanced telescopes, we're still left guessing about the true distribution of baryonic matter in these dusty regions. So, what can we do to overcome this challenge? One approach is to use telescopes that operate in the infrared spectrum, which can peer through the dust and reveal the hidden baryons. Another strategy involves studying the properties of cosmic dust itself, understanding how it forms, where it's concentrated, and how it interacts with light. By combining these insights, astronomers can develop better techniques to account for the obscuring effects of dust and uncover the missing baryons lurking behind it. As we continue to explore the role of cosmic dust in the missing baryon problem, we're reminded that even the smallest particles in the universe can have a big impact. Next, we'll delve into how plasma physics might hold the key to solving this cosmic mystery, adding yet another layer to our understanding of where the universe's missing matter could be hiding. Stay with us as we uncover more clues. Now, let's turn our attention to a realm that's as mysterious as it is fundamental to the universe: plasma physics. Plasma, often referred to as the fourth state of matter, is a hot, ionized gas that makes up a staggering amount of the visible universe. From the fiery cores of stars to the vast expanses of intergalactic space, plasma is everywhere. But how does this electrified gas tie into the missing baryon problem? The answer lies in its unique properties and the way it interacts with baryonic matter. Plasma is composed of charged particles, ions, and free electrons that behave very differently from the neutral atoms we're more familiar with. These charged particles are highly responsive to magnetic and electric fields, which means plasma can form complex structures and flow in ways that ordinary gases cannot. This dynamic behavior makes plasma incredibly difficult to study, especially when it comes to detecting the baryons hidden within it. The chaotic movements and interactions of plasma can scatter or absorb light, making it challenging to observe the baryons directly. One of the key challenges in understanding plasma's role in the missing baryon problem is its ability to trap and redistribute energy. In regions where plasma is dense, such as around galaxies or within galaxy clusters, it can heat up surrounding gas to extreme temperatures. This heated gas, often in the form of the warm, hot intergalactic medium, emits X-rays and other high-energy radiation. However, the plasma's turbulent nature can obscure these emissions, making it hard to pinpoint the exact location and quantity of baryons. Another intriguing aspect of plasma is its role in creating magnetic fields. These fields can influence the movement of charged particles, effectively hiding baryons by altering their paths or clustering them in ways that are difficult to detect. For example, magnetic fields can cause plasma to form filaments or sheets, which might contain significant amounts of baryonic matter. Yet, because these structures are often faint and spread out, they evade detection by traditional observation methods. So, how do we begin to unravel this cosmic puzzle? One approach is to use advanced simulations that model the behavior of plasma on cosmic scales. These simulations can help us predict where and how baryons might be hidden within plasma-rich regions. Additionally, telescopes equipped to detect X-rays and other high-energy emissions are crucial for peering through the plasma's veil. By combining these tools with a deeper understanding of plasma physics, we can start to piece together the role this electrified gas plays in the missing baryon problem. As we explore the complexities of plasma, we're reminded that the universe is full of surprises. Next, we'll dive into the quantum realm to see how the smallest particles in existence might hold clues to solving this cosmic mystery. Stay tuned as we uncover more layers of this fascinating puzzle. Now, let's venture into the fascinating world of quantum mechanics, where the rules of the very small might hold the key to understanding the very large. Quantum mechanics, the branch of physics that deals with the behavior of particles at the tiniest scales, has long been a cornerstone of our understanding of the universe. But could it also play a role in solving the missing baryon problem? The answer lies in the strange and often counterintuitive ways quantum effects manifest, even on cosmic scales. At the heart of quantum mechanics is the idea that particles don't behave like the solid, predictable objects we're used to. Instead, they exist in a state of probability, described by wave functions that dictate where they might be found. This probabilistic nature means that particles can exist in multiple states at once, a phenomenon known as superposition. On cosmic scales, this could mean that baryons might be distributed in ways that defy our classical understanding of matter. For instance, quantum fluctuations, tiny, random changes in energy, could cause baryons to clump together or spread out in patterns that are difficult to predict or observe. Another key quantum concept is entanglement, where particles become linked in such a way that the state of one instantly influences the state of another, no matter how far apart they are. While entanglement is usually discussed in the context of small particles, some theories suggest that it could have implications on much larger scales. If baryons are entangled in some way, their distribution across the universe might be influenced by these invisible connections, making them harder to detect using traditional methods. Quantum tunneling is another phenomenon that could play a role. This occurs when particles pass through barriers that, according to classical physics, they shouldn't be able to penetrate. On cosmic scales, this could mean that baryons might move through regions of space that we'd otherwise expect to block them, redistributing matter in ways that are hard to track. This could explain why some baryons seem to vanish from our observations. They might be hiding in places we can't easily see or predict. One of the most intriguing possibilities is that quantum effects might influence the way baryons interact with light. Quantum mechanics tells us that particles can absorb and emit energy in discrete packets called quanta. If baryons are interacting with light in ways that are governed by quantum rules, it could affect how we detect them. For example, baryons might emit or absorb light at wavelengths that are outside the range of our current telescopes, making them invisible to our instruments. So, how do we begin to explore these quantum clues? One approach is to develop new theoretical models that incorporate quantum mechanics into our understanding of cosmic structures. These models could help us predict where and how baryons might be distributed, taking into account the strange behaviors of the quantum world. Additionally, advancements in quantum technology, such as more sensitive detectors and telescopes, might allow us to observe these effects directly, bringing us closer to solving the missing baryon mystery. As we delve into the quantum realm, we're reminded that the universe operates on scales both vast and infinitesimally small. Next, we'll turn our attention to the cutting-edge tools that could finally uncover the missing Baryons' advanced telescopes. Stay with us as we explore how these technological marvels are pushing the boundaries of our cosmic understanding. Now, let's shift our gaze to the stars and the incredible tools that are revolutionizing our ability to explore the cosmos. Advanced telescopes like the James Webb Space Telescope are not just marvels of engineering, they're our best hope for finally uncovering the missing Baryons. These next-generation instruments are designed to peer deeper into space and with greater precision than ever before, offering us a clearer picture of the universe's hidden structures. The James Webb Space Telescope, often referred to as Webb, is a game-changer in the field of astronomy. Unlike its predecessors, Webb is equipped with infrared capabilities that allow it to see through cosmic dust and gas, revealing objects and phenomena that were previously invisible. This is crucial for detecting the warm-hot intergalactic medium, or WHIM, where many of the missing baryons are thought to reside. By capturing faint emissions from this elusive gas, Webb could provide the evidence we need to confirm its existence and distribution. But Webb isn't alone in this quest. Other advanced telescopes such as the Atacama Large Millimeter Array, or ALMA, and the upcoming Extremely Large Telescope are also playing pivotal roles. ALMA, for instance, specializes in observing millimeter and submillimeter wavelengths, which are ideal for studying cold gas and dust in the universe. These observations could help us trace the movement of baryons as they flow between galaxies and into the intergalactic medium, filling in gaps in our understanding of cosmic matter. One of the most exciting possibilities is that these telescopes might detect baryons in unexpected places. For example, they could reveal diffuse clouds of gas in the vast voids between galaxies or uncover hidden reservoirs of matter in the outskirts of galaxy clusters. By mapping these regions with unprecedented detail, we can begin to piece together the full story of where the missing baryons have been hiding. Another advantage of these advanced telescopes is their ability to observe the universe at different stages of its history. By looking at distant galaxies and quasars, we can study how baryons were distributed billions of years ago and compare that to their distribution today. This cosmic timeline could help us understand how baryons have evolved over time and why they seem to disappear in modern observations. Of course, the data from these telescopes is only as good as our ability to interpret it. That's why astronomers are developing sophisticated algorithms and models to analyze the vast amounts of information these instruments collect. By combining observations with theoretical predictions, we can refine our search and zero in on the most promising clues. As we continue to push the boundaries of technology and exploration, the missing baryons may not remain hidden for much longer. These advanced telescopes are not just tools, they're windows into the universe's deepest mysteries. And with each new discovery, we move closer to solving one of the greatest puzzles in modern cosmology. Next, we'll explore how interdisciplinary research is bringing together the brightest minds across fields to tackle the missing baryon problem from every angle. Stay tuned as we uncover the final piece of this cosmic puzzle. Now, let's take a step back and consider how the missing baryon problem isn't just a challenge for one field of science. It's a puzzle that requires collaboration across disciplines. The role of interdisciplinary research is becoming increasingly vital in our quest to solve this cosmic mystery. By bringing together the expertise of cosmologists, astrophysicists, and particle physicists, we're able to approach the problem from multiple angles, each offering unique insights that could lead to groundbreaking discoveries. Cosmology, for instance, provides the big-picture view of the universe's structure and evolution. It helps us understand how baryons might be distributed on the largest scales, from the cosmic web to the vast voids between galaxies. Astrophysicists, on the other hand, focus on the physical processes that govern the behavior of matter and energy in space. Their work helps us interpret observations from telescopes and simulations, shedding light on how baryons interact with their surroundings. Meanwhile, particle physicists delve into the fundamental nature of matter itself, exploring how baryons form and behave at the smallest scales. Together, these fields create a comprehensive framework for tackling the missing baryon problem. One of the most exciting aspects of interdisciplinary research is the way it fosters innovation. For example, techniques developed in particle physics, such as advanced detectors and data analysis methods, are now being adapted for use in astrophysics. These tools allow us to detect faint signals from distant galaxies or trace the movement of baryons through space with incredible precision. Similarly, insights from cosmology are helping particle physicists refine their models of how matter behaves under extreme conditions, such as those found in the early universe. Collaboration also extends beyond traditional scientific boundaries. Computer scientists and data analysts play a crucial role in processing the vast amounts of data generated by telescopes and simulations. Their algorithms help us identify patterns and anomalies that might otherwise go unnoticed, guiding us toward potential solutions. Even engineers contribute by designing the next generation of instruments, ensuring that we have the tools needed to explore the universe in ever greater detail. Perhaps the most compelling example of interdisciplinary success is the way it has transformed our understanding of the warm-hot intergalactic medium, or WHIM. By combining observations from X-ray telescopes, simulations of cosmic evolution, and theoretical models from particle physics, researchers have been able to piece together a clearer picture of this elusive gas. This collaborative effort has brought us closer than ever to confirming the existence of the WHIM and understanding its role in the missing baryon problem. As we look to the future, interdisciplinary research will continue to be at the forefront of this cosmic detective story. By pooling our knowledge and resources, we can tackle challenges that would be insurmountable for any single field. The missing baryons may still be hiding, but with the combined efforts of scientists from diverse disciplines, we're narrowing down the possibilities and inching closer to the truth. And with that, we've reached the end of our journey through the 25 clues to solving the missing baryon problem. But the story doesn't end here. Stay curious and keep exploring, because the universe still has plenty of secrets waiting to be uncovered. And so, we've journeyed through 25 fascinating clues in our quest to solve the missing baryon problem, a mystery that has puzzled scientists for decades. From the intricate structure of the cosmic web to the faint whispers of the warm-hot intergalactic medium, each clue has brought us closer to understanding where half the universe's matter might be hiding. We've explored how dark matter shapes the cosmos, how X-ray telescopes reveal hidden gas, and how simulations of the universe's evolution guide our search. We've even considered the role of supermassive black holes, cosmic winds, and the enigmatic behavior of plasma in the vastness of space. What makes this search so thrilling is not just the complexity of the problem, but the sheer ingenuity of the solutions being proposed. It's a reminder that science is a collaborative adventure where every discovery builds on the work of countless researchers across disciplines. The missing baryon problem isn't just about finding invisible matter. It's about pushing the boundaries of what we know and challenging ourselves to see the universe in new ways. As we wrap up this exploration, remember that the story of the missing baryons is far from over. New telescopes, advanced simulations, and groundbreaking theories are on the horizon, promising to shed even more light on this cosmic puzzle. So stay curious, keep asking questions, and most importantly, keep following the incredible journey of discovery as scientists around the world work to uncover the secrets of the universe. If you enjoyed this deep dive into one of cosmology's greatest mysteries, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update. The universe is full of wonders waiting to be explored, and together we can uncover them one clue at a time. Until next time, keep looking up.